Hello, and welcome to Space for Sleep. On a clear winter evening, the constellation Orion rises with a shape so familiar that many people recognize it before they remember the names of its stars. 3 points form the belt. A blue-white star shines near 1 foot. Above the belt, at the hunter's shoulder, another light carries a warmer color. It is not quite red, not quite orange, and never perfectly steady. This is Betelgeuse. To the unaided eye, it looks small enough to cover with the point of a needle. In reality, it is a star so large that ordinary comparisons begin to lose their meaning. Its visible surface would reach hundreds of millions of kilometers from its center. Its outer atmosphere extends farther still. It is losing matter into space. It brightens and fades. It swells and contracts. Enormous regions of hot gas rise through its surface and disappear again. Somewhere deep beneath those changing layers, nuclear reactions are carrying the star toward an ending that cannot be avoided. One day, Betelgeuse will collapse and explode as a supernova. That sentence is both certain and uncertain. The ending is certain because Betelgeuse was born with enough mass to build elements in its interior until the reactions that support it can no longer continue. The timing is uncertain because the surface we observe does not provide a simple clock for the hidden core. The explosion may be far beyond every human lifetime now beginning. It may occur sooner than the most conservative models suggest. And because Betelgeuse is hundreds of light years away, whatever we see tonight happened centuries ago. The title of this story contains a possibility that sounds dramatic. Betelgeuse could explode while you sleep. In the strictest physical sense, that is true. No astronomer can promise that the light of the explosion will not arrive tonight. But it does not mean that current evidence predicts an explosion tonight, this year, or this century. The more responsible statement is quieter and more interesting. Betelgeuse is an evolved massive star whose final collapse is inevitable, yet its exact internal stage remains uncertain. We are watching a stellar life near its end without knowing how near the final moment truly is. That uncertainty is not a failure of science. It is part of what makes Betelgeuse valuable. The star is close enough for astronomers to resolve details across its surface, bright enough for careful monitoring by small telescopes, complicated enough to challenge the best simulations, and late enough in its evolution to reveal how massive stars lose matter before they die. Every unusual change becomes a test. Every cycle of brightening and fading carries information. Every new instrument sees a different layer. And recently, Betelgeuse became even more complicated. For more than a century, some astronomers suspected that a hidden companion might orbit close to the supergiant and help produce one of its long brightness cycles. The companion was extraordinarily difficult to see beside the overwhelming glare of the supergiant. Then, in 2025, observations with Gemini North produced a probable direct detection in the predicted position. On July 28, 2026, astronomers published a much clearer result from very large telescope images obtained in December 2024, supplying the strongest evidence yet for the companion. Betelgeuse, the famous solitary shoulder of Orion, appears not to be alone. So tonight we will not treat Betelgeuse as a simple countdown to an explosion. We will follow the deeper story of how a point of reddish light became a measurable world, and why its distance and size are surprisingly difficult to determine. We will follow its transformation from a massive blue star into a red supergiant, the great dimming of 2019 and 2020, and the hidden companion that may explain a 6-year rhythm. Then we will move inward toward the nuclear furnace we cannot see, the signs that may arrive before core collapse, and what the supernova would actually mean for Earth. We begin where every observation begins, with old light entering the eye. When you look at Betelgeuse, you are not seeing the star as it is tonight. Estimates of its distance still differ because the star itself interferes with the measurement. Depending on the method, the distance is often placed somewhere between roughly 550 and more than 700 light-years. A useful conversational value is about 600 light-years, but the uncertainty should remain visible in our minds. At 600 light-years, the light reaching Earth tonight began its journey around the late Middle Ages. It crossed interstellar space while generations lived and died. While cities expanded, languages changed, telescopes were invented, and the nature of stars was discovered. The photons entering your eyes are not messages sent to a modern world. They left before anyone knew that Betelgeuse was a sphere of plasma, before anyone knew that Earth orbited the Sun, and before anyone could imagine a supernova as the collapse of a stellar core. This delay creates one of the most repeated ideas about Betelgeuse. Perhaps it has already exploded and we simply do not know. That is possible, but it is not a special prediction. Every distant object is seen in the past. If Betelgeuse remains intact in our sky, we know only that it remained intact when the light now arriving departed. Its present condition, in the ordinary Earth sense of the word present, cannot be known until later light reaches us. There is no contradiction here. Astronomers usually speak of what the star is doing now by referring to the latest observable state, because that is the only astronomical present available. The delay is built into every measurement. Yet Betelgeuse makes the delay feel unusually personal. This is not a faint galaxy seen as it was millions of years ago. It is a star many people can identify from a garden, balcony, field, or city street. It looks immediate. It looks local. And still, its image is centuries old. The star's name also arrives from the past, though by a much more tangled route. Betelgeuse comes through medieval manuscripts and European transliterations from Arabic words associated with the hand of Al-Jazza, a figure connected with the constellation we now call Orion. A copying error involving similar Arabic letters probably helped transform the word on its long journey into the modern name. The result has many pronunciations, none of which changes the star itself. Different cultures placed Betelgeuse inside different sky stories. Orion's shoulder is a useful Western description, but the reddish star existed in human imagination long before the modern constellation boundaries were fixed. Its color invited comparison with fire, blood, an arm, a shoulder, and changing seasons. Ancient observations are sometimes examined for clues that Betelgeuse may have appeared more yellow in the distant past, perhaps reflecting its evolution toward a cooler red supergiant state. Such historical color claims are intriguing, but they depend on texts whose words were not written as calibrated scientific measurements. They should be treated as clues rather than precise temperature records. What can be said with confidence is that Betelgeuse appears orange-red because its visible surface is cool by stellar standards. Its effective temperature is commonly placed around 3,500 Kelvin, with variations and model-dependent values. The Sun's visible surface is about 5,800 Kelvin. The lower temperature shifts more of Betelgeuse's light toward longer wavelengths, giving it the warm color that stands out beside the hotter blue, white stars of Orion. Cool does not mean weak. Betelgeuse radiates tens of thousands, perhaps around 100,000, times as much total energy as the Sun. Its brilliance comes from surface area. A square meter of its photosphere radiates less power than a square meter of the Sun's hotter photosphere. But Betelgeuse possesses an almost unimaginable number of square meters. The star has expanded until its radiating surface is vast enough to overwhelm the effect of its lower temperature. This is the first important lesson of Betelgeuse. Color, temperature, size, and luminosity are related, but they are not interchangeable. A cooler star can be far more luminous if it is sufficiently large. A star that looks like one modest point can be a swollen object large enough to contain the orbits of several planets. How large is it exactly? The honest answer is not one number. Modern models and measurements often place the radius in the broad neighborhood of 700 to 1,000 solar radii. One influential combination of astroseismology and stellar modeling estimated about 764 solar radii, while other studies adopt values closer to 1,000. The disagreement does not mean that telescopes are incapable. It means that Betelgeuse does not offer a sharp, quiet edge. The surface of the Sun is already not a solid boundary, but the solar photosphere is compact enough to define usefully. Betelgeuse is different. Its atmosphere is extended, dynamic, and strongly dependent on wavelength. A radio telescope measures a larger apparent disk than an instrument observing visible or infrared light. Molecules form above the photosphere. Dust appears farther out. Hot spots and cool regions shift the center of brightness. Giant convective structures make one side brighter than another. The star changes while it is being measured. Even the distance is entangled with this restless surface. Parallax normally works by measuring a nearby star's tiny apparent shift against distant background objects as Earth moves around the Sun. But if the bright pattern across Betelgeuse changes, the apparent center of the star can wander. That wandering can imitate or disturb the parallax signal. Radio measurements, optical astrometry, pulsation models, and interferometry therefore produce values that do not fall perfectly on top of one another. Rather than hiding the uncertainty, we can use it. Suppose the radius is near 800 times the Sun's. If Betelgeuse replaced the Sun, Mercury, Venus, Earth, and Mars would lie deep inside it. The visible surface would extend to the region between the orbits of Mars and Jupiter, perhaps close to Jupiter depending on the adopted radius. If a larger estimate is used, the photosphere approaches or passes Jupiter's orbit. There is no need to choose one dramatic boundary and pretend it is exact. The real picture is stranger. The star breathes. The definition of its edge changes with wavelength, and its outer gas continues beyond the visible disk. At this scale, light itself needs time to cross the star. The Sun's diameter is crossed by light in a little under 5 seconds. Betelgeuse may require about an hour, or somewhat longer, for light to cross the visible disk. A commercial aircraft traveling continuously would need several centuries to circle it. Earth is not merely small beside Betelgeuse. Earth would be a tiny object moving through an atmosphere whose largest convective patterns can rival the dimensions of our orbit. Betelgeuse was not born this way. A red supergiant begins as a massive star formed in a cold molecular cloud. Gravity gathers gas into dense fragments. A protostar grows by accretion. The center becomes hot and compressed until hydrogen nuclei can fuse into helium. For a star with perhaps 15 to 20 times the Sun's initial mass, the resulting main sequence life is bright, hot, and short. The phrase short life is relative. Betelgeuse is probably around 8 to 10 million years old. That is an immense interval compared with human history, yet it is brief beside the Sun's expected life of roughly 10 billion years before its own red giant transformation. Massive stars spend fuel quickly because their cores are hotter and their fusion rates rise steeply with temperature. They possess more fuel than the Sun, but they consume it at a vastly greater rate. Imagine two lamps. One contains more fuel but burns with a flame so powerful that it empties its reservoir quickly. The other glows gently for far longer. Betelgeuse is the first lamp. Its mass compressed the core, the compression raised the temperature, and the temperature accelerated nuclear reactions. The star shone with the extravagance of a life that could never be long. During its hydrogen-burning youth, Betelgeuse would have looked far bluer and more compact than it does now. Deep in the core, the fusion of hydrogen into helium released energy. That energy produced pressure, and the pressure balanced gravity. The balance is called hydrostatic equilibrium, but the word equilibrium should not suggest stillness. A star is an active balance. maintained by energy flowing outward while gravity pulls inward at every moment. As hydrogen in the central region became depleted, the balance changed. Fusion could continue in a shell around the exhausted core. The helium-rich core contracted and heated. The outer layers responded by expanding enormously. Expansion cooled the visible surface, shifting its color toward red. Betelgeuse became the supergiant we see. The transformation did not simply enlarge the old star, as if inflating a balloon. It reorganized the interior. The core and shells followed new nuclear paths. The envelope became deeply convective. Mass loss increased. The star's rotation, chemistry, magnetic behavior, and interaction with any companion all began to matter in new ways. We do not know every step in Betelgeuse's personal history. Its motion through space is relatively fast, and a curved bow shock has been detected where its stellar wind meets the surrounding interstellar medium. The star may have been ejected from a birthplace associated with the wider Orion region. Some models have suggested that an earlier merger could help explain why the surface appears to rotate faster than a simple isolated red supergiant model predicts. The newly detected present companion adds another piece, but it does not automatically explain every unusual property. Betelgeuse may have had a complicated family history long before we began watching it. What we see now is the result of all that history. A massive core hidden inside a dilute envelope so extended that the average density of much of the star is extraordinarily low. If you could remove a small volume from the outer layers and somehow hold it on Earth, it would not resemble solid material or ordinary air. It would be hot ionized gas, but far less dense than the atmosphere around you. Betelgeuse's enormous size does not mean every part is packed with matter. The mass is concentrated inward, while the outer envelope occupies a huge volume. This helps explain why the star can change shape and lose material. Gravity at the visible surface is weak compared with the Sun's. Convection, pulsation, radiation pressure, magnetic effects, and shocks can lift gas upward. Once material reaches cooler regions, molecules and dust grains may form. Radiation pushes on the dust, and collisions can help drag gas outward. The exact mechanism of red supergiant mass loss remains one of the important unsolved problems in stellar astrophysics. Betelgeuse is not simply waiting for death. It is actively constructing the environment into which its future explosion will expand. Every atom carried away by the wind becomes part of the circumstellar medium. Dense clumps, arcs, shells, and uneven outflows may surround the star. When the supernova shock eventually arrives, it will encounter this material. The collision can alter the early light, radio emission, X-rays, and spectral lines of the explosion. To understand the future supernova, astronomers must understand the present wind. And to understand the wind, they must watch the surface. For most stars, the word surface is already a simplification. For Betelgeuse, it is almost a negotiation. The visible photosphere is the layer from which light can escape without being repeatedly absorbed and scattered. It is not a crust. Gas moves through it. The apparent radius changes with wavelength because different atoms and molecules become opaque at different heights. Above it lies an extended atmosphere containing warm molecular layers, cooler gas, dust-forming regions, and a wind that continues into interstellar space. The best telescopes do not see Betelgeuse as a perfect circle. Interferometers combine light from separated telescopes to achieve the resolving power of a much larger instrument. With these techniques, astronomers have mapped bright and dark regions, measured changes in angular diameter, and watched asymmetries evolve. Radio arrays reveal structures in the extended atmosphere. Ultraviolet observations probe hot chromospheric gas. Infrared instruments follow molecules and dust. Each wavelength tells the story of a different height. On the Sun, convection produces millions of granules. each roughly the size of a country. Hot plasma rises in bright centers, cools, and sinks along darker boundaries. Betelgeuse may have only a handful of truly enormous cells dominating the visible disk at one time, accompanied by smaller structures. A single large cell can cover a substantial fraction of the star. It can remain influential for months or years. It can push material outward far more dramatically than ordinary solar granulation ever could. Three-dimensional simulations of red supergiants resemble boiling more than smooth breathing. Their surfaces deform. Shock waves pass through the atmosphere. Bright plumes rise, spread, and cool. Dark lanes move between cells. The center of brightness wanders even when the center of mass does not. This is one reason the star's distance is difficult to measure, and one reason simple one-dimensional models cannot reproduce every observation. The convection is slow only by comparison with human expectations of an explosion. Gas may move at many kilometers per second, but the star is so large that a structure can take months to cross a meaningful distance. A convective event can begin beneath the surface, rise through the envelope, alter the local temperature, and eventually contribute to an ejection whose dust becomes visible long afterward. Betelgeuse also pulsates. Its brightness is not constant. Long before the Great Dimming made international news, observers knew Betelgeuse as a semi-regular variable. Some of its changes repeat approximately, while others do not. The dominant familiar pulsation has a period near 400 days. A shorter cycle near 200 days can also appear, and a much longer variation around 2100 days, close to 6 years, has puzzled astronomers for decades. A pulsation is not the whole star switching on and off. The radius, temperature, opacity, and motion of the atmosphere change together. When the outer layers expand, they generally cool. When they contract, they heat. Changes in temperature alter the visible light strongly, especially for a cool star whose spectrum lies near the edge of the human eye's sensitivity. A small temperature change can therefore produce a noticeable visual change without requiring an equally large change in the star's total energy output. One mechanism that can drive pulsation is related to opacity in partially ionized layers. Gas that becomes more opaque traps radiation, heats, and expands. Expansion changes the ionization and allows energy to escape. The layer cools and contracts, beginning the cycle again. In a red supergiant, this mechanism interacts with turbulent convection, shocks, and enormous scale heights. The result is not a clock with one clean hand. It is a set of overlapping rhythms played by an unstable instrument. The roughly 400-day variation is widely interpreted as a fundamental radial pulsation mode. In that mode, the star expands and contracts in a global pattern. The shorter period may be an overtone. The long secondary period was harder to explain. Similar long cycles occur in many cool luminous stars, and proposed causes have included unusual pulsation modes, giant convective patterns, dust, rotation, and companions. For Betelgeuse, the companion idea gradually became testable. More than a century of brightness measurements showed the long rhythm. Spectroscopic observations also recorded changes in radial velocity, the motion toward and away from Earth inferred from shifts in spectral lines. When the phase relationship between brightness and velocity was analyzed carefully, some researchers found that an orbiting object could explain the pattern more naturally than a simple pulsation. The predicted companion would be close to the supergiant on the sky, separated by only a few hundredths of an arcsecond at the most favorable point in the orbit. It would also be drowned in Betelgeuse's glare. Detecting it was like trying to see a small lamp beside a searchlight from a great distance, except that the searchlight itself was boiling, changing shape, surrounded by gas, and bright at many wavelengths. Models published in 2024 used the long period to predict where the companion should appear near maximum separation late that year. Observers aimed high-resolution instruments at the system. In 2025, a team using the Gemini North Telescope and a speckle imaging camera reported a probable direct detection at the expected location. The team proposed the name Sawara, an Arabic word meaning her bracelet, echoing the origin of the name Betelgeuse as the hand of Al-Jaza. The first detection was important, but the signal was difficult. Then came a stronger result. On July 28, 2026, astronomers reported their analysis of images obtained with the Sphere instrument on the Very Large Telescope in December 2024. Advanced processing revealed a source at the predicted separation and position. The observations provided the clearest image and strongest evidence, yet that Betelgeuse has a close stellar companion. Although the scientific paper still used careful language and called it a candidate pending another observation on the opposite side of the star. The new interpretation changed the long-period story. The 6-year rhythm no longer needed to be treated as a mysterious deep pulsation of Betelgeuse itself. The orbiting star could influence the gas and dust around the supergiant, perhaps creating a wake, changing extinction, or affecting measured velocities as it moves through the complex circumstellar environment. The companion also matters for estimates of Betelgeuse's evolutionary stage. A controversial model had interpreted the 2100-day cycle as the star's fundamental radial pulsation. Such a long fundamental period would require a much larger radius and could place Betelgeuse in a very late carbon-burning stage, potentially only decades or centuries from collapse. But if the long cycle is orbital, as the companion evidence strongly suggests, the approximately 400-day cycle remains the better candidate for the fundamental mode. That supports a smaller radius and an earlier internal stage, likely core helium burning in several influential models. This does not settle every question. The mass and nature of the companion have been revised as observations improve. Early predictions favored a much lower mass star. The 2026 VLT analysis, assuming both stars formed together, found that the detected source could correspond to a star roughly 2.6 to 3.1 times the mass of the Sun, considerably more massive than the earliest orbital estimates suggested. More observations are needed. The next favorable geometry will allow astronomers to test whether the source follows the predicted orbit. The companion is not expected to prevent Betelgeuse from becoming a supernova. It may affect mass loss, angular momentum, the circumstellar environment, and the interpretation of variability. Over long periods, close binary interactions can profoundly alter stellar evolution. But the current orbit appears wide enough that Betelgeuse remains recognizably a red supergiant evolving toward core collapse. The discovery is a reminder that even one of the most observed stars in the sky can hide another star in plain sight. And it arrived only a few years after Betelgeuse delivered its most famous surprise. During the northern autumn of 2019, the star began to fade. Betelgeuse had faded many times before. Variable star observers expected it to move through bright and dim phases. Amateur astronomers had contributed decades of careful visual estimates and photometric measurements. A dimming alone was not alarming. What changed was the depth. By December, Betelgeuse was fainter than its normal cycle suggested. Through January and into early February 2020, the decline continued. At minimum, its visual magnitude reached roughly 1.6, the faintest value in the modern photometric record. The familiar shoulder of Orion looked weakened. People who knew the constellation could see the difference without equipment. The timing was almost designed to attract attention. A famous star, already known as a future supernova, was suddenly behaving in an unprecedented way. News reports asked whether the explosion had begun. Social media carried images of Orion with a noticeably dim Betelgeuse. Astronomers answered cautiously. The star was unusual, but there was no evidence that its core was collapsing. That distinction matters. The visible surface of a red supergiant can change dramatically for reasons unrelated to the final nuclear crisis. Convection can create cool regions. Pulsation can lower the temperature. Material can be ejected and condense into dust. None of these surface events requires the core to be within days of collapse. Yet the Great Dimming was not ordinary. It gave astronomers a rare chance to watch a large mass loss event unfold across the resolved face of another star. Images taken with the Very Large Telescope showed that the southern portion of Betelgeuse became much darker than the rest. The star did not simply fade uniformly like a lamp turned down. Its apparent shape changed, and a large part of the disk lost visible brightness. Spectra and ultraviolet measurements supplied additional pieces. Months before the deepest minimum, the Hubble Space Telescope had detected unusually hot, dense material moving outward through the atmosphere. The sequence suggested that a large convective upwelling or shock lifted part of the photosphere. Material traveled away from the star, expanded, and cooled. Once temperatures became low enough, dust grains could form. A cloud along our line of sight then blocked some visible light. At the same time, Betelgeuse was approaching a natural low point in its pulsation. The photosphere cooled. The cooler region produced less visible light, and the ejected material added extinction. The best current picture is therefore not one cause, but a combination. A major surface mass ejection, local cooling, dust formation, and the timing of the normal variability. Different observations emphasized different parts of this explanation. High-resolution visible images strongly support a cool patch associated with dust. Multi-wavelength data from the Himawari 8 weather satellite, unexpectedly useful because Betelgeuse happened to fall within its field, indicated that both cooling and increased dust extinction contributed substantially. Mid-infrared interferometry showed that dust models and cool spot models could both reproduce aspects of the data. Science did not reduce the event to one simple cartoon. It assembled a physical sequence from many imperfect views. The phrase surface mass ejection was chosen partly to distinguish the event from the smaller coronal mass ejections familiar on the Sun. Betelgeuse appears to have lost an enormous piece of photospheric material, many times the mass involved in an ordinary solar event. Estimates vary because the geometry and density are uncertain, but the ejected mass may have been several times the mass of the Moon. That comparison should not suggest that a moon-sized solid fragment broke away. The material was hot. Diffuse plasma spread across a huge volume. Still, by the standards of observed stellar surface events, it was extraordinary. It may have removed hundreds of times more mass than a typical solar coronal mass ejection. As the cloud cooled, dust grains formed and shaded part of the star. The grains were not black smoke in an earthly sense. They were microscopic solids, likely silicate-rich in the oxygen-dominated environment, suspended in expanding gas. They absorbed and scattered visible light. At infrared wavelengths, they could emit thermal radiation. By April 2020, Betelgeuse had brightened again. The supernova had not arrived. The dramatic public question seemed answered. The Great Dimming was not the final collapse. But the scientific story continued. After the ejection, the star's familiar 400-day pulsation weakened or became difficult to trace. A shorter, roughly 200-day rhythm became more prominent. The atmosphere remained disturbed. Betelgeuse experienced unusual brightness behavior, including a bright phase in 2023. Researchers described the star as slowly recovering from the event, as though a giant bell had been struck so strongly that its normal vibration changed. This is more than metaphor. A violent surface disturbance can alter the phase and amplitude of oscillations in the envelope. The Great Dimming gave astronomers a natural experiment. Watch a red supergiant before, during, and after a major ejection, then compare the pulsation modes and atmospheric velocities. The event also helped solve a broader problem. Red supergiants must lose large amounts of mass before they explode, but their surfaces are not hot enough for radiation alone to drive winds in the same way as hotter massive stars. Dust can absorb radiation efficiently, yet the photosphere is often too warm for dust to form close to the star. Something must first lift gas outward into cooler regions. Giant convection and shocks may provide that lift. The Great Dimming showed one plausible route in real time. A plume rises, gas cools, dust condenses, starlight pushes on the grains. The grains transfer momentum to surrounding gas. Material escapes. The process is probably irregular rather than spherical. Betelgeuse does not peel away in smooth layers. It throws clumps, creates arcs, and fills its surroundings unevenly. The hidden companion may add wakes or local disturbances. The future supernova will therefore not expand into empty space or a perfectly symmetrical wind. It will meet a landscape built by the star's final centuries and millennia. The Great Dimming was not evidence that Betelgeuse would explode within days. It was evidence that dying massive stars can change their own surroundings through sudden, localized acts of mass loss. That is a quieter conclusion than the headlines offered, but it is scientifically richer. It also forces us to ask a more difficult question. If the surface can behave so dramatically without the core collapsing, what would a genuine warning look like? The problem is that a star's most decisive events occur where light cannot escape directly. Betelgeuse is opaque. Photons created in deep layers are absorbed, re-emitted, and scattered countless times before their energy reaches the surface. The light we see tells us mainly about the photosphere and atmosphere, not the immediate condition of the core. Surface pulsations carry indirect information, but interpreting them requires models of convection, rotation, mass, composition, distance, and radius. A small change in one assumption can move the predicted star to a different stage of evolution. This is why the original short description of Betelgeuse as an onion with an iron core already in the center is too confident. The onion structure is a useful picture of a massive star near the very end, but we do not know that Betelgeuse has reached that final arrangement. If it already possessed a growing iron core, collapse would be extremely close. Most widely supported models do not place it there. The more conservative and influential interpretation puts Betelgeuse in core helium burning. In this stage, the central temperature is high enough for helium nuclei to combine through the triple alpha process, producing carbon. Additional reactions create oxygen. Hydrogen continues to fuse in a shell outside the core. The star can remain in this phase for hundreds of thousands of years, although the exact remaining lifetime depends on how much helium has already been consumed. A different study published in 2023 argued that Betelgeuse might be in a late stage of core carbon burning and perhaps only decades to centuries from collapse. The claim drew great attention because it offered a dramatically shorter clock, but the result depended on identifying the long 2100-day brightness cycle as a fundamental radial pulsation. That interpretation required a radius around 1300 solar radii, larger than many direct observational constraints. Other researchers challenged the model, and the companion evidence now offers a persuasive orbital explanation for the long cycle. The debate is valuable because it shows how stellar ages are inferred. No instrument can descend through Betelgeuse and sample the core. Astronomers compare observed luminosity, temperature, surface composition, radius, pulsation periods, rotation, and mass loss behavior with families of evolving computer models. A model that matches several properties may still fail another. Convection is often represented with simplified prescriptions. Rotation and binary history add uncertainty. The result is not a single timestamp, but a range of plausible states. At present, it is safer to say that Betelgeuse has exhausted hydrogen in its core, has become a red supergiant, and is probably burning helium centrally or has progressed somewhat beyond that in ways not yet settled. It is not safe to say that silicon is definitely burning around an inert iron core right now. The final advanced stages will come, but the surface has not told us that they have arrived. Understanding those future stages explains why the final clock accelerates so violently. Hydrogen fusion is efficient enough to support a massive star for millions of years. Helium burning is shorter. Carbon burning may last hundreds or thousands of years, depending on mass and conditions. Neon burning can last about a year. Oxygen burning may last months. Silicon burning may persist for only days. The exact durations vary across models, but the pattern is firm. Each new fuel supports the star for less time. The reason lies partly in nuclear binding energy. Fusion releases energy when lighter nuclei combine into more tightly bound nuclei. The process continues through a sequence of elements, but the energy gained per reaction changes. In advanced stages, much of the energy escapes in neutrinos rather than heating the star. The core must burn fuel faster to maintain pressure against gravity. Neutrinos are nearly massless particles that interact only weakly with matter. In the Sun, neutrinos created by fusion escape directly from the core and reach Earth in about 8 minutes. In a massive evolved star, thermal processes generate vast neutrino losses. As the core grows hotter, neutrino emission becomes a dominant cooling channel. The star's visible luminosity may not change dramatically while its hidden nuclear clock accelerates. After helium, carbon, and oxygen remain in the core. If the star is massive enough, contraction raises the temperature until carbon can ignite. Carbon fusion produces elements such as neon, sodium, and magnesium. Later contraction enables neon burning, then oxygen burning, and finally silicon burning. Multiple shells may operate at once, with older fuels burning farther out and newer fuels closer to the center. Only near the end does the familiar onion diagram become appropriate. An iron group core surrounded by shells rich in silicon, oxygen, neon, carbon, helium, and hydrogen. Even then, the boundaries are not neat classroom lines. Convection mixes material. Shells can merge or fluctuate. Waves travel outward. Burning can be asymmetric. The star is a three-dimensional turbulent object, not a diagram printed in layers. Iron changes everything. Fusion of light elements up to the iron region can release energy. Fusing iron into heavier nuclei consumes energy rather than supplying it. Once an iron-rich core grows, nuclear fusion can no longer provide a new central fuel capable of halting contraction. Electron degeneracy pressure contributes support, but the core gains mass from the surrounding silicon-burning shell. When the core approaches its effective stability limit, several processes remove support almost together. High-energy photons break iron nuclei apart, consuming energy in photodisintegration. Electrons are captured by protons, producing neutrons and neutrinos. The loss of electrons weakens electron degeneracy pressure. Gravity wins. The core collapses at a substantial fraction of the speed of light. In less than a second, a region thousands of kilometers across contracts toward a neutron star scale of only a few tens of kilometers. Density rises beyond that of atomic nuclei. The inner core stiffens and rebounds. A shock wave forms, but it initially loses energy while breaking apart infalling nuclei and producing neutrinos. The simple picture of a core bouncing and blasting the star apart is incomplete because the shock can stall. The enormous neutrino flux from the newborn compact object helps revive the shock. Convection, turbulence, and asymmetric flows behind the shock also contribute. Modern simulations work to reproduce how these effects combine in 3 dimensions. The exact mechanism remains a major area of research, but observations and theory agree that many red supergiants end as core collapse supernovae. Most of the gravitational binding energy released in the collapse leaves as neutrinos. The optical light, brilliant as it will appear, represents only a small fraction of the total energy. For several seconds, the core will outshine the rest of the visible universe in neutrinos, though those particles will pass through almost everything unnoticed. The shock must then travel outward through the enormous envelope of Betelgeuse. This journey takes time. A red supergiant can be hundreds of millions of kilometers in radius. Depending on the structure and the exact collapse, the shock may require hours or perhaps longer to reach the visible surface. When it emerges, shock breakout releases a brief pulse of high-energy radiation and intense ultraviolet light. The expanding envelope then brightens at optical wavelengths. This gives neutrino observatories a remarkable advantage. Neutrinos from the collapsing core escape almost immediately, while the shock is still crossing the star. Detectors on Earth may therefore know that Betelgeuse has collapsed before ordinary telescopes see the explosion. The world already has a network designed for such a moment. The Supernova Early Warning System, known as SNEWS, connects neutrino detectors in different countries. A nearby core collapse supernova would produce simultaneous bursts in several instruments. By requiring coincidence, the network can issue an alert while reducing false alarms. Astronomers could turn telescopes toward the source and capture the earliest electromagnetic stages. For a supernova in another galaxy, neutrino detections may number in the tens, hundreds, or thousands depending on distance and detector size. For Betelgeuse, the count could be enormous. Different estimates depend on the true distance, neutrino properties, collapse physics, detector technology, and whether the final object is a neutron star or black hole. Existing and future detectors could record tens of thousands to millions of interactions across the global network. Water Cherenkov detectors watch for faint flashes created when neutrino interactions produce charged particles moving through water. Liquid scintillator detectors measure bursts of light in another medium. Argon detectors are especially sensitive to electron neutrinos. Ice Cube at the South Pole would see the overall glow of many interactions across its vast instrumented ice, even if individual events are not resolved in the same way. Together, the detectors would sample different flavors and energies. Before the collapse itself, there may be another warning. During the final carbon, neon, oxygen, and silicon burning stages, the hot core emits increasing numbers of low-energy neutrinos. These pre-supernova neutrinos are far fainter than the collapse burst, but may be detectable from a very nearby star. Betelgeuse is one of the best candidates. Depending on its mass, distance, burning stage, neutrino ordering, and detector sensitivity, a statistically significant rise could appear hours before collapse, and in favorable circumstances perhaps earlier. The warning would not necessarily be a public countdown lasting weeks. Current realistic systems are more likely to provide hours, with sensitivity improving as detectors grow. A 2026 study discussing future detection strategies described warning times of roughly up to 12 hours for a Betelgeuse-like case under particular assumptions. Other calculations produce different windows. The essential point is that the hidden core may announce its crisis through neutrinos before the surface changes. If such an alert arrived, professional and amateur observatories would begin continuous monitoring. Space telescopes would face practical restrictions because Betelgeuse is extremely bright. Ground-based instruments would prepare filters, spectrographs, polarimeters, radio arrays, X-ray satellites, gravitational wave searches, and neutrino analyses. Some facilities would risk saturation. Others would use small apertures or indirect observing methods. Ordinary cameras could become scientifically useful. The first message might be invisible to human eyes. A neutrino alarm reporting that something had happened beneath Orion's shoulder. Then the waiting would begin. The exact delay between neutrino burst and visible brightening would measure the time required for the shock to cross the envelope. That interval would constrain the radius and internal structure of Betelgeuse more directly than many present methods. A very early ultraviolet or X-ray pulse would reveal shock breakout. Its duration and color would test models of the atmosphere and the materials surrounding the star. The circumstellar gas created by centuries of mass loss would immediately matter. The shock and radiation could ionize nearby wind material before the main ejecta reached it. Narrow spectral lines might appear and change rapidly. Dust could be heated or destroyed. The hidden companion would suddenly find itself inside an expanding radiation field and later within supernova debris. Because Betelgeuse is so close, astronomers could observe details normally blended into one unresolved point. Interferometers might track asymmetry in the expanding photosphere. Polarization would reveal departures from spherical symmetry. Neutrino arrival times and energies would probe matter at nuclear density. Gravitational wave detectors might search for signatures of asymmetric core motion, rotation, or instabilities. No supernova in human history has been observed with this combination of instruments from before collapse onward. The famous supernova in the Large Magellanic Cloud in 1987 provided the first confirmed neutrinos from a stellar explosion. Only a few dozen events were detected in instruments not built with modern supernova networks in mind. Those detections transformed astrophysics. Betelgeuse would be far closer, and today's detectors are far more capable. Yet we should return to the uncertainty that began this story. The ability to describe the final collapse does not tell us when it will occur. A red color is not a countdown. A large size is not a countdown. A dust cloud is not a countdown. A brightening is not a countdown. Even a change in pulsation may result from surface disturbance rather than core evolution. The only truly decisive warning may come when the advanced nuclear stages produce detectable pre-supernova neutrinos, followed by the collapse burst itself. Before that, estimates remain statistical and model-dependent. This makes the phrase "could explode tonight" both true and misleading. It is true because probability cannot be reduced to zero, and because the light may already be traveling toward us. It is misleading if heard as evidence that astronomers expect the explosion tonight. They do not. The most defensible expectation is that Betelgeuse probably has a very long time left by human standards, perhaps tens or hundreds of thousands of years. But the range is broad enough, and the consequences spectacular enough, that the star remains under constant attention. There is no visible clock on its surface. There is only evidence, arriving one layer at a time. And when the decisive evidence comes, it will transform the sky. To imagine the supernova accurately, we should first remove a common cinematic picture. Betelgeuse will not suddenly expand across half the sky as a fiery sphere. Even at maximum brightness, the exploding star will remain too small for the unaided eye to resolve. It will look like a point of light. The shock and ejecta will be enormous in physical size, but hundreds of light years of distance compress them into a stellar point. The change will be in brightness, color, and duration. Before collapse, Betelgeuse is already one of the most familiar bright stars. After shock breakout and expansion, the luminosity may rise by many orders of magnitude. Models of a Betelgeuse like Type II supernova give a range of possible apparent magnitudes, often somewhere around -8 to -12, depending on explosion energy, radius, distance, extinction, and the amount of radioactive nickel produced. At the brighter end of plausible estimates, It could reach a substantial fraction of the full moon's apparent brightness, perhaps approaching half in especially luminous models. At the fainter end, it would still be far brighter than Venus and easily visible in daylight. Comparing a point source with the moon can be confusing. The moon spreads its light across a disk half a degree wide. Betelgeuse would concentrate comparable or somewhat lower total brightness into an unresolved point. It would be dazzling to look at, but not a miniature sun. At night, it could cast shadows. Whether those shadows are strong depends on the peak brightness and local conditions, but the supernova would plainly illuminate landscapes. Orion would no longer look balanced. A brilliant point at the shoulder would dominate the constellation and perhaps the entire night sky. In daylight, finding it would require knowing where to look and keeping the sun safely out of view. Against a blue sky, the point could remain visible for weeks. People would photograph it near buildings, mountains, and clouds. The event would be seen by billions, though not by everyone at the same moment because Orion's visibility depends on season, latitude, weather, and the time of day when the explosion brightens. The title says while you sleep because the first optical light could arrive while much of Earth is asleep. In another hemisphere, people might be awake under daylight. News would travel faster than the star's brightness changed. By the time someone stepped outside after an alert, the point might already be rising. The light curve would not be a single flash. After the shock reaches the surface, the outer envelope expands and cools. Hydrogen in the ejecta recombines as the temperature falls, releasing stored energy and helping maintain a broad plateau in visible brightness. A classic Type 2P supernova can remain bright for around 100 days. Betelgeuse may produce this general type, though details of its mass loss, remaining hydrogen envelope, companion, and explosion energy could modify the curve. The early color would likely be very blue because the expanding material begins extremely hot. Over days and weeks, the photosphere would cool and shift through white, yellow, and redder tones. Spectral lines would broaden because different parts of the ejecta move toward and away from Earth at thousands of kilometers per second. Radioactive nuclei created in the explosion would power later stages. Nickel-56 decays into cobalt-56, which decays into iron-56. Gamma rays and positrons deposit energy in the expanding debris. As the ejecta thin, the decline rate reveals how efficiently that energy remains trapped. The amount of nickel helps determine the brightness of the radioactive tail. The light would carry a layered record of the star. Early spectra would sample the outer hydrogen-rich envelope and circumstellar gas. Later spectra would reveal deeper products as the ejecta became transparent. Oxygen, calcium, iron group elements, and other material forged during the star's life and explosion would appear in emission lines. Betelgeuse would no longer be a hidden interior wrapped in an opaque envelope. The supernova would tear the structure apart and display its chemistry across time. That destruction is also creation. Elements made during the star's life would be thrown into interstellar space. The explosion and neutrino-rich environment would contribute additional nuclei. The expanding remnant would mix the products into the surrounding medium, where future clouds could form new stars and planets. The iron in blood, calcium in bone, oxygen in air, and many heavier elements have histories connected to earlier generations of stars, though not all came from the same type of explosion. Betelgeuse's death would be a local example of the process that made rocky worlds possible. Would any of this harm Earth? No credible model places Betelgeuse close enough for its supernova to become a mass extinction threat. The uncertainty in distance matters for measuring radius and luminosity, but not for this conclusion. Whether the star is roughly 550, 600, or more than 700 light-years away, It remains far beyond the distance at which high-energy radiation and cosmic rays are expected to cause severe global biological damage. Nearby supernova hazards are complicated. The effect depends on explosion type, orientation, interstellar magnetic fields, cosmic ray transport, the surrounding medium, and the spectrum and duration of X-rays and gamma rays. Older popular summaries often quoted a dangerous distance of about 30 light-years. More recent atmospheric and cosmic ray modeling suggests that serious effects may extend to roughly 60 or perhaps over 100 light-years under some conditions, while the strongest biospheric threat remains much closer. Betelgeuse lies several times farther away even than these expanded concern ranges. Its visible brilliance would not mean that destructive energy was reaching Earth. Human eyes are highly sensitive, and an enormous stellar luminosity can appear spectacular at a distance, while the energy per square meter remains modest compared with sunlight. The supernova would not heat the climate, ignite forests, or burn anyone outdoors. The sun would still dominate daytime energy. Even a full moon-like point at night supplies vastly less illumination than daylight. People might sleep with brighter skies, notice shadows, and experience a sky unlike any in recorded history, but ordinary light from the event would be physically harmless. Ultraviolet and X-ray radiation would increase above background levels, especially during early phases, yet the atmosphere would absorb much of the high-energy component. At Betelgeuse's distance, predicted ozone effects are small. There is no reason to seek shelter or protective clothing because of the supernova, or avoid looking at the night sky. The point source could be uncomfortable through a large telescope if observed carelessly, just as the moon can be dazzling at high magnification, but it would not damage unaided vision in the way the sun can. Astronomers would use filters and short exposures mainly to protect instruments from saturation and to obtain useful measurements. Cosmic rays would be a slower story. Charged particles do not travel straight from the supernova at light speed. Galactic magnetic fields scatter them, stretching their arrival over centuries or millennia. Depending on the local magnetic connection, Earth might eventually receive an elevated cosmic ray flux. At hundreds of light years, it would not be expected to create a global catastrophe. There is also no known danger from the neutron star's possible radio beam. If the remnant becomes a pulsar and one of its beams sweeps across Earth, we would detect radio or high-energy pulses. The beam is not a weapon cutting through space. At this distance, it would be an astronomical signal. A gamma-ray burst is similarly not expected. Long-duration gamma-ray bursts are associated with particular rapidly rotating massive stars, often stripped of their hydrogen envelopes and found in different environments. Betelgeuse is a hydrogen-rich red supergiant, and there is no evidence that its rotation and structure are suitable for a tightly beamed gamma-ray burst directed at Earth. The explosion would be safe enough to enjoy and close enough to revolutionize science. That combination is rare. After the bright plateau and radioactive decline, the human sky would slowly return toward darkness. Betelgeuse would fade from daylight visibility, then from easy naked eye visibility. Orion would change permanently. The shoulder star that anchored the pattern for thousands of years would be gone as a steady red point. For a while, the supernova itself might remain visible to the unaided eye. The remnant would not immediately resemble the Crab Nebula. Every supernova expands into a different environment and produces a different compact object. The arcs and bow shock around Betelgeuse, the clumpy wind from the great dimming and other ejections, and the presence of the companion would shape the aftermath. What would remain at the center? A neutron star is a likely outcome for a star with Betelgeuse's estimated mass, but the word certainly should be avoided. The relation between a star's initial mass and its final compact remnant is not one simple boundary. Mass loss, core structure, rotation, metallicity, binary interaction, and the strength of the explosion all matter. Some models could permit substantial fallback, in which material initially ejected later falls back onto the compact object. Enough fallback could form a black hole. If a neutron star forms, it will contain perhaps more mass than the Sun compressed into a sphere about the size of a city. Matter will be supported by neutron degeneracy and nuclear forces. The magnetic field may be intense. Rapid rotation could produce a pulsar, though the beam may not point toward Earth. Even without a visible pulsar, X-rays and the surrounding wind nebula might reveal the object. If a black hole forms promptly or through fallback, the neutrino signal and explosion may differ. A sudden cutoff in neutrinos could mark the formation of an event horizon. The optical supernova could be weaker or otherwise altered, though black hole forming collapses span a range of possibilities. The companion would face a violent transition. Before the explosion, Sawara orbits within the extended environment of Betelgeuse, close enough to interact with gas and perhaps create a wake. When the primary loses a large fraction of its mass, the gravitational system changes suddenly. The companion may be flung into a new orbit or released as a runaway star. Supernova ejecta will strike it, strip or heat part of its atmosphere, and deposit unusual elements on its surface. Because the companion seems to be much less massive and far fainter, it would survive the explosion as a normal star unless the interaction is unusually destructive. Long after Betelgeuse vanished, Sawara might move away carrying a chemical scar from the event. This possibility gives the system an unexpected emotional shape. Betelgeuse may not die alone. A young companion could witness the collapse at close range, survive, and continue through the galaxy after the famous red star is gone. The future remnant would also become a laboratory for cosmic distances. Its known location, bright pre-explosion observations, and detailed monitoring would connect the properties of a red supergiant progenitor directly to the resulting supernova. Usually, astronomers identify progenitors only in archival images of distant galaxies, often as a few pixels. Betelgeuse has been imaged across wavelengths, resolved across its disk, monitored spectroscopically, and measured for more than a century. No other supernova progenitor has such a biography. We know its brightness cycles, atmospheric motions, surface asymmetries, molecular layers, dust, wind, bow shock, mass ejections, likely companion, and debated internal state. When it explodes, every one of those pre-existing observations will become part of the supernova dataset. The Great Dimming will be reinterpreted yet again. Researchers will ask whether the 2019 surface mass ejection resembled the eruptions in the final years before collapse, or whether it was an ordinary event for a red supergiant with a long remaining life. The disturbed pulsation after 2020 will be compared with the final pre-supernova behavior. The companion's orbit will help constrain the mass lost in the explosion. A century of amateur observations will matter too. Betelgeuse is so bright that it can be monitored without a professional observatory. Variable star observers compare it with nearby stars or use cameras and photometers to build long light curves. These records reveal cycles longer than individual research grants, and sometimes longer than the careers of the astronomers who analyze them. Professional surveys often avoid the brightest stars because detectors saturate. Small telescopes can succeed where giant instruments struggle. This inversion is one of the charming features of Betelgeuse science. A backyard observer can contribute to the same light curve used to study one of the largest stars known. If Betelgeuse begins an unusual change tonight, amateur measurements may document it before a major observatory receives time to respond. During the Great Dimming, the public attention was dramatic, but the underlying data depended on patient observation begun long before anyone knew the event would occur. The next important behavior may not look spectacular. A slight shift in a spectral line, a change in ultraviolet emission, a new dust feature, or a disrupted pulsation period could reveal a process that models failed to predict. The companion's predicted reappearance on the other side of Betelgeuse will provide another test. Long baseline interferometers will improve maps of the surface. New space missions may observe the star indirectly even when its brightness makes normal imaging difficult. That is why the history of measuring Betelgeuse matters. Astronomers did not learn its nature from one decisive image. They learned it by adding techniques that each removed a different kind of blindness. A century ago, astronomers began turning that layered point into a measurable disk. In 1920, Albert Michelson and Francis Pease used an interferometer attached to the 100-inch Hooker telescope at Mount Wilson to measure Betelgeuse's angular diameter. The method separated incoming starlight along different paths and recombined it, creating interference fringes. As the separation changed, the visibility of the fringes revealed the angular size of the source. Betelgeuse became the first star beyond the Sun whose diameter was measured in this direct way. The achievement was less like photographing a clear circle and more like inferring the width of something from the behavior of waves, but it opened a new kind of astronomy. Stars were no longer only points with spectra and brightness. At least a few giant stars could be given apparent dimensions. The early diameter did not settle the physical size because distance remained uncertain and because different wavelengths sampled different layers. Later interferometers improved resolution and showed that the disk was not uniform. Infrared observations found bright regions. Millimeter and radio measurements traced larger, cooler structures. Adaptive optics corrected atmospheric blurring. Space telescopes observed ultraviolet flows that no ground-based optical image could reveal. Every improvement made Betelgeuse less like a sphere in a textbook. Spectroscopy had already shown that the star's atmosphere contains molecules such as titanium oxide, whose absorption bands strongly influenced the red supergiant spectrum. Molecular layers extend above the conventional photosphere, creating what astronomers sometimes call a hemisphere. Water vapor, carbon monoxide, silicon monoxide, and other species occupy different regions. Their spectral lines carry velocities, temperatures, and chemical abundances. The atmosphere is simultaneously cool enough for complex molecules and marked by patches of much hotter chromospheric gas. This coexistence is difficult to explain with one smooth temperature profile. Shocks in magnetic activity may heat local regions. Convection can carry energy unevenly. The outer atmosphere resembles a weather system on a scale larger than the inner solar system. Betelgeuse has a weak surface magnetic field, detected through subtle polarization in spectral lines. Weak is relative to compact magnetic stars, but even a field of about a Gauss spread across a supergiant surface may influence plasma and mass loss. The field is likely tangled and variable, generated or organized by convection rather than by a simple solar-like dynamo. Magnetism may help lift gas or guide flows, but observations do not yet yield one complete wind mechanism. Pulsation sends shocks outward. Convection creates plumes. Molecules form. Dust condenses. Radiation accelerates grains. The companion perturbs surrounding material. Each process may contribute at different times and locations. The rate at which Betelgeuse loses mass is also uncertain and variable. Typical estimates are around a few millionths of a solar mass per year, though the value depends on assumptions about wind speed, gas-to-dust ratio, geometry, and clumping. At such a rate, the star can shed a substantial fraction of the Sun's mass over hundreds of thousands of years. The wind is slow compared with the winds of hot blue stars. Gas may flow outward at roughly 10 to 20 kilometers per second. That is far faster than any terrestrial wind, but modest besides supernova ejecta. The future shock will overtake centuries of wind within a relatively short time, converting kinetic energy into radio, X-ray, and optical emission. Farther out, infrared images reveal arcs and a bow-shaped structure ahead of Betelgeuse's motion through space. The bow shock forms where the wind meets the interstellar medium. Betelgeuse is moving relative to the surrounding gas, so the encounter is stronger on the forward side. Material piles up, heats, and cools into curved features. The bow shock may lie several light years from the star. That scale tells us that Betelgeuse has been shaping its surroundings for a long time. The immediate wind reflects recent centuries. The larger arcs preserve older interactions and perhaps changes in mass loss as the star evolved from a hotter phase into a red supergiant. Some observations also suggest a straight bar-like feature beyond the bow shock. It may be an unrelated interstellar filament or a remnant boundary associated with an earlier blue supergiant wind. The interpretation remains uncertain. Betelgeuse's environment, like its surface, refuses to become one clean diagram. Rotation adds another puzzle. Measurements have indicated that the outer atmosphere may rotate at several kilometers per second. For such an expanded star, that can be surprisingly fast. Conservation of angular momentum normally slows rotation dramatically when a star grows from a compact main sequence body into a red supergiant, much as a spinning skater slows by extending the arms. One explanation is that Betelgeuse merged with a companion in the past, gaining angular momentum. Another is that giant convective cells can imitate the spectral signature of rotation. Three-dimensional simulations have shown that a boiling surface may produce velocity patterns that look like organized spin when observed with limited resolution. The current small companion could also influence measurements, but is unlikely by itself to explain every proposed rotational property. The debate illustrates a recurring problem. Astronomers see light integrated through a turbulent atmosphere and must decide whether a pattern represents global rotation, local convection, orbital motion, pulsation, or some combination. Betelgeuse can create false simplicity. A clean sinusoidal velocity curve may hide an orbit. A red-blue gradient may hide a convective cell. A change in apparent radius may reflect opacity rather than physical expansion. The star teaches caution because it is close enough to expose the ways distant red supergiants can mislead us. Most red supergiants in other galaxies are unresolved points. Their mass loss rates, temperatures, and radii are inferred from broad spectra and light curves. If Betelgeuse's apparent properties can shift because one side cools or a dust clump crosses the line of sight, similar stars may also vary in ways that bias estimates of supernova progenitors. This became especially relevant after several supernovae were observed to have dense material very close to their progenitors. Early spectra sometimes show narrow emission lines that disappear within days, indicating gas expelled shortly before collapse. Other red supergiants brighten or erupt in the years before death. The final burning stages may generate waves that carry energy into the envelope and enhance mass loss. Could Betelgeuse's great dimming have been such a pre-supernova eruption? Possibly in the broad sense that it resembles processes that can occur late in massive star lives. But no evidence connects the 2019 event uniquely to the final nuclear stages. Large convective ejections may occur throughout the red supergiant phase. One event cannot establish a countdown. Astronomers therefore search for patterns rather than isolated drama. Does the mass loss rate increase persistently? Do eruptions become more frequent? Does the pulsation period change in a way consistent with rapid structural evolution? Do spectra reveal new elements mixed to the surface? Do neutrino detectors see the rising thermal flux of advanced burning? Most surface changes are ambiguous. The core neutrino signal would be much harder to imitate. Another possible clue could come from gravity waves generated by violent convection in late-burning shells. These waves can travel into the envelope, deposit energy, and perhaps drive outbursts years before collapse. Models differ on how effectively the energy reaches the surface. If Betelgeuse eventually shows repeated powerful ejections, astronomers will compare them with wave-driven mass loss predictions. Yet even then, the final answer may arrive only with collapse. The difficulty resembles listening to a building from outside while machinery operates in a sealed basement. Vibrations reach the walls. Air vents change temperature. Lights flicker. Some signs reflect normal operation. Others could indicate failure. Without direct access, the diagnosis depends on models and multiple sensors. Betelgeuse provides many sensors, but the basement remains sealed. Astroseismology is one way to listen. In the Sun, thousands of oscillation modes allow precise reconstruction of internal rotation and sound speed. Betelgeuse offers only a few broad, irregular periods, blurred by convection and limited observations. The newly identified orbital contribution removes one confusing signal, but it does not turn the star into a clean musical instrument. The approximately 400-day pulsation still constrains mean density. In simple terms, larger and lower density stars pulsate more slowly. Matching the observed period helps estimate radius and mass. The shorter overtone adds another constraint. But the relation depends on the envelope structure, and the great dimming disturb the modes. The star's changing rhythm may itself become useful. If the fundamental mode returns after the surface ejection, its recovery time will test models of damping and excitation. If it does not return in the expected form, the event may have changed the envelope more deeply than assumed. The companion complicates and clarifies at once. It complicates because orbital motion, wakes, dust, and blended light enter the measurements. It clarifies because the 6-year cycle no longer needs to be forced into a pulsation model that implies an implausibly large radius. A hidden star solved one mystery by creating several new questions. How did the companion survive the expansion of Betelgeuse? Is it orbiting just outside the visible photosphere or within the extended atmosphere? Does it accrete gas? Does it carve a spiral pattern in the wind? Does its radiation destroy dust locally? Has it transferred angular momentum? Will it remain bound after the supernova? High-resolution observations over a full orbit can answer some of these questions. The source should move along the predicted path. Its spectrum can reveal temperature and mass. H-alpha emission may show interaction with gas. Changes in Betelgeuse's long-period brightness can be compared with the companion's orbital phase. This is why the 2026 result belongs near the center of the story rather than as a footnote. Betelgeuse is no longer best understood as one isolated star with 3 unexplained pulsation periods. It is a turbulent red supergiant in a close binary environment, and at least one major long cycle is likely created by the relationship between the 2 stars. The discovery also changes the title's emotional image. The star that could explode while you sleep has a neighbor moving through its outer realm. The future explosion will not occur in solitude. The companion is part of the pre-supernova system and may become a witness carried into the aftermath. Betelgeuse has already been studied by instruments designed for other purposes. A weather satellite watched the great dimming in multiple infrared bands. Solar and Earth observing systems sometimes include bright stars in calibration or background data. Archival observations can become valuable only after a later event gives researchers a reason to search them. This makes the star a meeting place of technologies. Optical telescopes measure brightness. Spectrographs identify molecules and velocities. Infrared instruments trace dust. Radio arrays map extended gas. Ultraviolet observations reveal chromospheric activity. X-ray telescopes constrain hot plasma and the companion. Polarimetry tests asymmetry and magnetic structure. Neutrino detectors wait for the core. Gravitational wave observatories wait for the collapse. No one instrument sees Betelgeuse. Each sees a partial star. The visible point in Orion is the combined result of layers that do not behave in the same way. A cool photosphere emits most of the familiar light. A warm molecular envelope changes apparent size. A chromosphere contains unexpectedly hot gas. Dust absorbs and re-radiates energy. A wind carries matter outward. A companion moves through the environment. A hidden core evolves on a different clock. When the Great Dimming occurred, one wavelength could suggest cooling, another dust, another outward motion. Only the combination produced a coherent account. To appreciate how unusual this opportunity is, we can look backward at the supernovae humans have already seen. In the year 1006, observers across several regions recorded a new star of extraordinary brightness. It may have been the brightest stellar event in recorded history, though it was a different kind of supernova, probably the thermonuclear destruction of a white dwarf. In 1054, a new star appeared in the constellation now containing the Crab Nebula. Chinese and other records describe its visibility in daylight. The remnant contains a pulsar spinning about 30 times per second. In 1572, Tycho Brahe studied a new star in Cassiopeia. Its lack of measurable parallax showed that change could occur beyond the moon, challenging the old belief in an unchanging celestial realm. In 1604, Kepler observed another galactic supernova. No confirmed naked-eye supernova has appeared in the Milky Way since then, though explosions hidden by dust may have occurred. Supernova 1987A appeared in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. It was visible to the unaided eye from the southern hemisphere, but it never approached the brightness expected for Betelgeuse. Its neutrinos arrived before the optical discovery and gave the first direct evidence that core collapse releases enormous energy in neutrinos. These events changed astronomy because the sky changed visibly. Modern people are accustomed to receiving discoveries as images on screens. A new exoplanet, galaxy, or black hole may be scientifically profound but remain invisible without specialized data. Betelgeuse would be different. The event would be both a global public spectacle and a precision scientific experiment. People would see it before understanding it. Children would learn a sky in which Orion had a brilliant temporary shoulder. Artists would paint it. Religious and political interpretations would appear despite scientific explanations. Conspiracy theories would spread alongside neutrino alerts and spectra. Airlines might dim cabin lights so passengers could look. Cities might organize observing nights. Phones would struggle to capture the brightness, while professional cameras used exposures lasting fractions of a second. The supernova would become part of ordinary conversation because it would be impossible to ignore. Yet the experience would differ across Earth. If the optical rise occurred when Orion was near the sun in the sky, the first days might be dominated by daylight observations and specialized instruments. If Orion were visible at night, the transformation could be immediate. Northern and southern observers would see the constellation from different angles. Clouds might hide the event from some regions at peak. People living under severe light pollution would still see it because the star would overwhelm city glow. The supernova would not remain at maximum forever. Its slow fading would create a shared calendar. People might remember where they were when the neutrino alert arrived, when the point became visible in daylight, when it first failed to cast shadows, and when it finally disappeared from unaided sight. Astronomers would remember different milestones: the first shock breakout detection, the first spectrum, the first gravitational wave candidate, the first resolved asymmetry, the transition to the radioactive tail, the emergence of forbidden emission lines, and the first evidence for the compact remnant. This event may happen long after every person alive today is gone. The thought does not make Betelgeuse less interesting now. It changes the relationship. We are not necessarily an audience waiting for a scheduled performance. We may be one generation in a long line of observers watching a star through a stage that lasts far longer than human history. The great dimming briefly made the star feel urgent. The companion discovery made it feel newly knowable. Both events demonstrate that Betelgeuse can surprise us without exploding. That may be the real value of the waiting. A star does not need to die to reveal how stars die. Its winds show how mass is lost. Its dust shows how gas escapes. Its pulsations test internal structure. Its companion reveals how binary motion can mimic a stellar rhythm. Its surface ejection demonstrates how irregular the last phases can be. Its uncertain distance exposes the limits of astrometry for a moving photosphere. Its disputed core stage tests the assumptions inside evolutionary models. Betelgeuse is already an experiment in stellar death, even while it remains alive. There is another reason the uncertainty deserves patience. The phrase dying star can make the present seem like a brief final moment. But a red supergiant phase may last around 100,000 years or more. The star can be genuinely near the end in a cosmic sense, and still have a remaining life longer than recorded human civilization many times over. Cosmic nearness is not human nearness. The Sun is about halfway through a main sequence life of roughly 10 billion years. 1,000,000 years is a small fraction of that life. For Betelgeuse, 100,000 years may be part of the final chapter. For us, it is an almost unimaginable future. This difference in timescale is why honest language matters. Calling the star about to explode may be acceptable when discussing stellar evolution, but it becomes misleading if translated into a calendar prediction. Astronomers can identify the route without knowing the distance remaining. Betelgeuse will explode. Betelgeuse is not known to be on the verge of exploding. Both sentences can be true. The first follows from its mass and evolutionary state. The second follows from the absence of decisive evidence that advanced burning has reached the final hours, days, or years. Holding both ideas together is more satisfying than replacing uncertainty with drama. We can now return to Orion with a different eye. The red point is not a fuse visibly burning down. It is the photosphere of a star whose core is hidden, whose surface is turbulent, whose atmosphere reaches far into space, whose light carries a centuries-old image, and whose companion was concealed until modern high-contrast techniques separated it from the glare. What appears simple is layered. While astronomers study that orbit, they continue watching the ordinary brightness of Betelgeuse. Ordinary is the wrong word, because the star does not repeat itself exactly. A long light curve resembles overlapping waves with noise, sudden deviations, and seasonal gaps. When Orion lies near the Sun, visual estimates from different observers carry personal biases, but large numbers can be combined. Electronic photometry is more precise, but can saturate and may not span as many decades. The American Association of Variable Star Observers preserves observations made by professionals and amateurs. A person can learn the nearby comparison stars, estimate Betelgeuse's brightness, and contribute a point to a century-long record. The act is simple. Look, compare, record. The scientific value emerges from continuity. This continuity matters because a red supergiant's changes are slow by human standards, but fast by stellar standards. A 6-year orbit is longer than many research projects. A convective cell may survive across observing seasons. A mass loss arc may record centuries. The final red supergiant phase outlasts institutions and nations. No single astronomer will watch the whole story. The data must remember what people cannot. If Betelgeuse remains a red supergiant for another 100,000 years, future observers may inherit light curves far longer than any existing astronomical record. Instruments will change beyond recognition. The star's angular surface may be mapped routinely. Neutrino observatories may detect advanced burning long before collapse. Or civilization may lose the continuity and begin again with only fragments of old data. The photons will continue arriving regardless. This indifference is part of the calm of astronomy. Betelgeuse does not know that it is famous, does not hurry because we are watching, and does not owe our generation the explosion. Its nuclear clock proceeds according to density, temperature, composition, and gravity. The great dimming happened during our brief window. The companion was found during our brief window. Those discoveries are enough. They reveal a star more alive than the fixed constellation suggests. The most important near-term test of Betelgeuse may therefore be quieter than a supernova. It may be a small point of light appearing where orbital calculations say it should appear. The route to that point began with a rhythm. Betelgeuse has a familiar variation of roughly 400 days, but it also brightens and fades on a much longer cycle of about 6 years. Long secondary periods occur in many cool, luminous stars, and for decades they resisted one universal explanation. Some may involve pulsation, others dust or convection, and some may involve companions. In Betelgeuse, the long cycle was accompanied by changes in radial velocity and in the measured position of the star's center of light. Those different clues began to line up as one orbital problem. 2 studies published in 2024 used long records of brightness, velocity, and astrometry to predict that a companion should reach a favorable separation from Betelgeuse near the end of that year. The predicted angle was tiny. Even at maximum apparent separation, the 2 objects would be divided by only a few hundredths of an arcsecond. Betelgeuse itself is a resolved, changing disk rather than a clean point, so the expected companion lay close to the distorted edge of a blazing and unstable source. The Gemini North observations reported in 2025 used speckle imaging. Instead of taking one long exposure through Earth's moving atmosphere, the instrument recorded many extremely short exposures. The changing atmospheric distortion could then be characterized and partly removed. A faint source appeared close to the expected location in the 2024 data, while an earlier observation taken when the companion should have been hidden in projection did not show the same source. The agreement was intriguing, but the statistical detection was modest. The result was described as probable rather than final. It matched the predicted separation, direction, brightness difference, and observing geometry, yet one difficult image beside a boiling supergiant could not end a century of doubt by itself. The Very Large Telescope result reported in July 2026 was much stronger. The SPHERE instrument had observed Betelgeuse in December 2024, near the favorable part of the proposed orbit. SPHERE was designed partly to isolate very faint objects close to bright stars. It combines adaptive optics, careful control of scattered light, and observing modes developed for difficult high-contrast imaging. Months of processing revealed a distinct source close to the predicted position. This was direct imaging in the literal astronomical sense. Light attributed to the candidate companion was separated from the overwhelming light of Betelgeuse. The image was clearer than the Gemini result and carried far less room for accidental structure. The research team nevertheless retained the word candidate. A true companion should continue around the orbit and appear on the other side of Betelgeuse at the predicted time. A fixed artifact, background source, or transient surface structure would not trace that path. This future test is unusually satisfying because it is simple in principle. Take another difficult image. Measure where the source appears. Compare the new position with the orbit predicted before the observation. If it moves as required, the evidence becomes not merely a close match in one epoch, but a measured piece of an orbit. The new images also changed the expected nature of the companion. Early dynamical models often favored an object with a mass similar to or below that of the Sun. The brightness in the VLT data, interpreted under the assumption that the two stars form together, instead points toward a companion around 2.6 to 3.1 solar masses. That would make Betelgeuse be more massive and intrinsically brighter than originally expected, though still almost lost beside the red supergiant. This difference is not a small bookkeeping correction. A companion's mass controls the orbit, the transfer of angular momentum, the strength of tides, and the way it interacts with Betelgeuse's wind. It also affects whether both objects can plausibly share the same age. Betelgeuse evolved quickly because it began with high mass. A companion only a few times the mass of the Sun could still appear young, while the much heavier primary had already become a red supergiant. The companion seems to orbit at a distance comparable with the outer part of our solar system. Yet Betelgeuse is so swollen that this is only a few stellar radii. The smaller star may travel through the extended atmosphere and wind rather than through clean, empty space. Gas flowing away from Betelgeuse can be focused, disturbed, or drawn into a wake behind the companion. Spectroscopic work published in early 2026 found variations in circumstellar absorption and chromospheric outflow that follow the proposed orbital period. The pattern was interpreted as possible evidence of an expanding wake. This does not prove every detail of the model, but it connects the 6-year clock with matter moving around the star, not merely with a change in visible brightness. The orbit may also help explain why Betelgeuse appears to rotate faster than a simple isolated red supergiant model would predict. Tidal interaction can exchange angular momentum between an orbit and a stellar envelope. Earlier models even suggested that Betelgeuse may have swallowed another companion in the past. The newly imaged candidate does not prove that older merger story, but it shows that binary interaction cannot be treated as an optional footnote. At the same time, the companion should not be turned into a new source of certainty. We do not yet know its precise orbit, spectrum, age, radius, or long-term fate. We do not know whether the current mass estimate will remain unchanged after cleaner observations. We do not know how deeply its gravity reorganizes the outflow or whether it affects only local gas near its path. Some orbital models predict that the companion could eventually spiral inward and be engulfed by Betelgeuse. Earlier estimates placed such an event thousands of years in the future, but those calculations assumed a different companion mass and an uncertain structure for the supergiant. The new images require the models to be run again. It would be premature to attach a precise countdown to an orbit that has not yet been fully traced. The same caution applies to the supernova. The companion does not provide a date for core collapse. Its greatest immediate effect is interpretive. If the 6-year cycle is orbital, it should not be used as the fundamental pulsation period of Betelgeuse. That removes much of the support for the unusually large radius and very late carbon-burning state proposed in the most dramatic short lifetime model. In this way, finding another star makes Betelgeuse's explosion seem less immediate rather than more. The result does not push the supernova backward with a physical force. It changes which observations should be used to infer the hidden core. The companion may become scientifically important again when the explosion finally occurs. Sudden mass loss from Betelgeuse will alter the gravitational bond between the two objects. The supernova may also give the compact remnant a kick. Depending on the direction and strength of that kick, the system could remain bound, become highly eccentric, or break apart. Betelgeuse B might continue beside a neutron star or black hole, or it might depart as a runaway star carrying a record of the former binary. Before then, it can serve as a moving probe of the outer atmosphere. Its orbit crosses regions filled with gas, dust, shocks, and changing radiation. By watching absorption and emission vary with orbital phase, astronomers may map material that would otherwise be difficult to separate along the line of sight. The companion therefore adds a second clock to the story. The 400-day pulsation measures the breathing of the supergiant. The 6-year orbit measures a relationship between two stars. The much longer evolutionary clock measures the slow transformation of the core. Only the final neutrino burst will announce that the last clock has run out. For the next few years, the orbital clock is the one astronomers can test most directly. It asks a clear question and promises an observable answer. Betelgeuse does not need to explode to produce a historic result. A faint companion completing a predicted arc beside its surface may be enough. Until then, the final event remains hypothetical, and the current star remains worthy of attention on its own. You can see Betelgeuse without knowing any of this. Find Orion. The three-belt stars are the easiest guide. Above them, on one side, is Betelgeuse. On the opposite side below the belt is Rigel, much hotter and bluer. The color contrast is often clearer when you look slightly away rather than directly, allowing the eye's sensitive peripheral vision to help. Betelgeuse is best placed in the evening sky during the winter months of the northern hemisphere and the corresponding summer months in the southern hemisphere. From Spain, much of Europe, North America, North Africa, and large parts of Asia, Orion rises in the east during autumn evenings, dominates winter nights, and moves westward into spring. From southern latitudes, the constellation appears rotated but remains prominent. No telescope is required. Binoculars do not reveal a disk because the apparent diameter is far below their resolution, but they intensify the color. A small camera can record changes in brightness over time if exposures are calibrated and compared carefully. The star's magnitude may vary enough for a patient observer to notice across months. Compare it with nearby stars rather than relying on memory. Bellatrix is usually fainter and bluer. Procyon, Aldebaran, and Rigel provide other references, though atmospheric extinction and color differences complicate visual estimates. Looking low above the horizon can make Betelgeuse appear to flicker and change color because Earth's atmosphere refracts different wavelengths through turbulent cells. That twinkling is not the star physically changing second by second. When Orion climbs higher, the image steadies. This distinction offers another lesson. Not every change belongs to Betelgeuse. Some belong to Earth's atmosphere, some to instruments, some to the observer, some to the companion, and some to the star itself. Astronomy is the work of separating these layers. The Great Dimming was real because many independent observers and instruments measured it. The companion is persuasive because it appeared where orbital models predicted and was recovered with different techniques. The core stage remains uncertain because no available measurement uniquely chooses one model. Evidence has different strengths. A peaceful night beneath Orion can therefore become an exercise in scientific thinking. The star looks red. That observation suggests a cool photosphere. Its brightness at a large distance implies enormous luminosity. Interferometry provides angular size. Pulsation supplies density information. Spectra reveal composition and motion. Dust changes the wavelength dependence of dimming. Orbital motion creates periodic velocities. Neutrinos will eventually reveal the core. One point of light becomes a network of inferences. There is no need to wait for the supernova to feel the scale of the object. The photons arriving now have crossed centuries. The visible disk, if placed in our solar system, would swallow the inner planets. The gas we see at the surface may have risen through convective structures larger than Earth's orbit. The companion is moving near the outer edge of that vast atmosphere. The wind has built arcs light years away, and deep inside, the star is producing new elements from old ones. If core helium burning is the correct present stage, 3 helium nuclei, are combining to form carbon through a process that would be extraordinarily unlikely at ordinary density and temperature. Some carbon captures additional helium to produce oxygen. These two elements will dominate the eventual core composition before later burning stages begin. Carbon and oxygen are not abstract products. They are central to rocky planets and life as we know it. The star's interior is changing the chemical inventory of the galaxy, though much of that material remains locked inside until winds or the supernova release it. The outer atmosphere already returns processed matter to space. Convection and earlier mixing have altered surface abundances, bringing products of hydrogen burning into observable layers. Spectra show nitrogen enrichment and changes in carbon and oxygen ratios consistent with evolved massive star models. The star's death will release deeper material, but it will not distribute every element equally. Some falls into the compact remnant. Some escapes in different velocity layers. Some nuclei are made explosively as the shock changes temperature and density. The exact yield depends on the explosion and fallback. Betelgeuse is therefore not only dying, it is manufacturing and sorting matter. The word death can obscure this continuity. A supernova destroys the star as a stable luminous object, but its matter continues. The companion continues. The remnant continues. The shock continues. New stars may eventually form from enriched gas. Even the photons continue, moving outward as a spherical shell of information. If the supernova occurred today at Betelgeuse, Earth would see it centuries later. Worlds farther away would see it later still. There is no single moment when the whole galaxy knows the star has died. The explosion moves through space-time as news carried by light, neutrinos, gravitational waves, and particles. Somewhere on the far side of Betelgeuse, an observer at the right distance could already see an event that Earth will not see for centuries. Somewhere closer to us along another direction, the old red supergiant light may still be arriving long after Earth has watched the supernova. The star's history is distributed across space. This is true of every astronomical event, but Betelgeuse makes it easy to imagine because the delay is comparable to recorded human history. When tonight's light left the star, no one had built a telescope. When the light from the great dimming left, Earth was still centuries from naming the event. When the companion's present position becomes visible to future observers, our current scientific papers may be historical documents. We live inside the delay. That is why the question "has it already exploded" cannot be answered and does not need to be answered. In the only observable sense available to us, Betelgeuse is still there. Its old light is real light. Its measured surface is a real state. Astronomy is always the study of the past, and the past is how the universe becomes knowable. The uncertainty does not make the observation unreal. It makes every photon an arrival. There is one more reason Betelgeuse deserves to be watched patiently. The star can connect observations made at completely different scales. A change noticed by a person with the naked eye may begin as motion inside a convective cell. The rising gas can alter ultraviolet spectral lines, cool at the photosphere, move outward through molecular layers, form dust visible in the infrared, and eventually join a radio-emitting wind. Months or years later, the same material may become part of a circumstellar arc that a future supernova shock will cross. Few astronomical objects allow one physical disturbance to be followed through so many stages. The Great Dimming demonstrated this chain imperfectly but vividly. Photometric observers measured the loss of visible light. High-resolution images showed that the southern part of the disk darkened disproportionately. Ultraviolet spectra recorded outward moving hot material before the deepest fading. Infrared observations tested whether newly formed dust was present. Later pulsation measurements showed that the envelope did not immediately return to its earlier rhythm. No single dataset contained the full explanation. The story emerged because the observations overlapped in time. This is why astronomers continue building coordinated campaigns. Betelgeuse cannot be studied most effectively by giving one telescope a few isolated hours. The surface changes across weeks, the pulsation across hundreds of days, the companion across about 6 years, and the bow shock across much longer intervals. The instruments must be connected by calendars as well as wavelengths. Future campaigns may use optical interferometers to reconstruct images every few weeks, while radio arrays map the larger atmosphere. Spectrographs can measure gas rising and falling at different heights. Polarization can reveal the distribution of dust and magnetic fields. High-contrast imagers can trace the companion's orbit. Precise photometry can separate pulsation from orbital modulation. The observations will also improve the supernova prediction indirectly. A better orbit constrains the system's total mass. A better distance improves luminosity and physical radius. A reliable radius narrows pulsation models. Surface abundances constrain mixing and evolutionary history. A more accurate mass loss rate changes estimates of how much hydrogen envelope remains. None of these measurements will produce a guaranteed date. Together, however, they can replace a very broad range of models with a smaller one. Science often advances by narrowing uncertainty rather than eliminating it. Betelgeuse is particularly good at showing why this narrowing can be difficult. The quantities depend on one another. Distance affects luminosity. Luminosity affects the inferred mass and evolutionary track. Radius affects pulsation interpretation. Pulsation interpretation affects the proposed internal stage. The companion affects the long-period signal. Convection affects the apparent center used for astrometry. Dust affects the brightness used to judge pulsation. A mistaken assumption can travel through the entire chain. The dramatic carbon-burning claim illustrated this sensitivity. Treat the 6-year variation as a radial pulsation, and the required radius becomes enormous. Accept that radius, and a very advanced evolutionary model can fit. Interpret the same 6-year variation as an orbit, supported by direct imaging, and the foundation of the near-term collapse argument weakens. The star itself did not change between the two interpretations. The map of causes changed. This is not embarrassment for astronomy. It is the normal process of testing hidden mechanisms against new evidence. The companion was difficult to detect precisely because the original problem was hard. Once found, it improved more than one part of the model. The next observation may do the same elsewhere. A clearer distance may settle the physical radius. A full orbit may determine the companion's mass. A recovered pulsation mode may constrain the envelope after the great dimming. A new ultraviolet ejection may reveal whether the 2019 event was exceptional or part of a recurring pattern. Even a non-detection can matter. If X-ray observations fail to see expected emission from accretion onto the companion, that limits how much gas the smaller star captures. If no strong magnetic structure appears, models that rely heavily on magnetism become less likely. If pre-supernova neutrinos remain absent, the result does not prove that collapse is distant, but it rules out the brief final stages within the detector's sensitivity at that time. Betelgeuse is therefore watched not because every change is an alarm, but because every change sorts the possible explanations. The public may ask one question: is it about to explode? The observations answer many quieter questions first. How does a giant cell lift gas? Where does dust condense? How does a companion move through a supergiant wind? Which period is a pulse and which is an orbit? How does a surface recover after losing an enormous plume? How much of the apparent rotation is real? By the time the final question is answered, these quieter answers will determine how well we understand the explosion. What, then, has Betelgeuse actually taught us before the explosion? It has taught us that the final lives of massive stars cannot be understood from smooth spheres alone. A one-dimensional model can calculate pressure, temperature, composition, and nuclear burning through time. Such models are essential. They explain why massive stars leave the main sequence, why red supergiant envelopes expand, and why an iron core eventually becomes unstable. But Betelgeuse shows everything that one dimension hides: giant convection, asymmetric ejections, patchy dust, wandering brightness, uncertain edges, magnetic structures, and a close companion moving through the outer environment. The star has taught us that stellar radius can be a physical question rather than one fixed measurement. In visible light, the disk has one size. In the infrared, molecules modify the apparent boundary. At radio wavelengths, the atmosphere appears larger. A star can have several useful radii, each describing a different layer. It has taught us that parallax, one of astronomy's cleanest geometric methods, becomes difficult when the object being measured has a shifting center of light. Betelgeuse is so nearby and so large that its own surface weather can compete with the tiny apparent movement produced by Earth's orbit. It has taught us that dimming does not automatically mean dying. The Great Dimming looked like a possible final warning to the public, yet observations revealed a surface ejection, cooling, and dust. The event was not a failed supernova. It was a successful experiment in mass loss. It has taught us that old periodic mysteries can conceal companions. The 6-year variation was discussed as a pulsation for decades. Careful analysis predicted a hidden orbit, and high-resolution imaging found a source where the companion should be. A star too faint to see beside Betelgeuse nevertheless changed the apparent rhythm of one of the brightest stars in the sky. It has taught us that a dramatic claim about the core must agree with the surface geometry. Interpreting the long cycle as a fundamental pulsation produced a late carbon-burning star with a very large radius and a near-term supernova. The companion interpretation removes the need for that radius and restores the stronger case for an earlier internal stage. The likely answer became less sensational and more consistent. And it has taught us how valuable uncertainty can be when it is described honestly. The distance is uncertain, so different observations are compared. The radius is uncertain, so wavelength-dependent layers are studied. The evolutionary stage is uncertain, so pulsation models, surface abundances, and binary history are tested. The wind mechanism is uncertain, so mass ejections are followed across the ultraviolet, visible, infrared, and radio spectrum. An uncertain object can become a productive object because every uncertainty points toward a measurement. Betelgeuse is sometimes introduced only through size. It is one of the largest familiar stars. If placed at the Sun, it would engulf Earth. Those facts are memorable, but size alone is not what makes the star scientifically exceptional. Its real importance comes from proximity, brightness, complexity, and timing. It is close enough for its surface to be resolved, bright enough for observations extending across centuries, large enough for convection to operate on scales unavailable in the Sun, evolved enough to be losing mass rapidly, complicated enough to contain both pulsations and orbital effects, stable enough that we can study it now, yet destined for a collapse whose physics we understand in outline, but have never observed at such close range. Few objects connect so many parts of astronomy in one place. The star's ancient motion connects it with stellar birth and possible ejection from an association. Its mass connects it with nuclear evolution. Its giant envelope connects it with convection and pulsation. Its wind connects it with dust chemistry and the interstellar medium. Its companion connects it with binary dynamics. Its future collapse connects it with neutrinos, gravitational waves, nuclear matter, supernova remnants, and the chemical evolution of galaxies. A person looking at Orion sees none of those divisions. The eye receives one warm point. That point is enough. For most of human history, nobody knew why Betelgeuse was red. People knew only that its color differed from nearby stars, and that Orion returned with the seasons. The star served as a marker in stories, calendars, navigation, and memory. Then spectroscopy turned color into temperature and composition. Physics turned brightness into luminosity. Interferometry turned a point into a disk. Long light curves turned irregular change into multiple periods. Space telescopes turned a dimming into an ejection. High-contrast imaging turned a 6-year rhythm into evidence for a companion. The history of Betelgeuse is therefore also a history of learning how to see. Each instrument removes one kind of blindness and reveals another. The first diameter measurement showed that a star could be resolved, but not what the surface was doing. Modern images showed dark and bright regions, but not the core. Neutrinos will eventually reach the core, but only during the final crisis. There will always be a hidden layer until the next messenger arrives. Perhaps the most beautiful part of the story is that the final collapse will reverse the direction of this investigation. Today, astronomers work inward from the light. Surface, atmosphere, pulsation, model, inferred core. During the supernova, information will rush outward from the center. Neutrinos will escape first. The shock will cross the star. Radiation will break through the surface. Spectra will peel back the ejecta over time. The hidden structure will reveal itself through destruction. The star will answer the question of its core by ceasing to be the star we knew. But that answer does not belong to any promised generation. The answer may still arrive tonight. Nature does not consult our preferred timetable, and no surface measurement can guarantee that the decisive light is not already traveling toward Earth. But possibility is not prediction. The evidence now available does not support a short countdown. The 400-day pulse, the dust of the Great Dimming, and the 6-year orbit belong to the visible and extended star. They reveal activity, structure, and change, but none of them is a clock reading from an iron core. The most widely supported models still leave Betelgeuse an immense interval by human standards. That does not make the star less dramatic. It makes the drama larger than an explosion. Tonight, the surface may be rearranging itself through convection. A plume may be rising through layers so wide that light takes a meaningful time to cross them. Dust may be forming beyond the photosphere. The companion may be traveling through the extended wind, leaving a wake that future spectra will detect. Deep inside, helium or later fuels continue the slow work that gravity will eventually finish. All of this is happening inside one orange-red point in Orion. When you find the 3 stars of the belt and move your eyes toward the shoulder, you are receiving light that began its journey centuries ago. You cannot know whether Betelgeuse still looks exactly the same at this moment. You can know what the arriving light contains. It contains the signature of a cool surface radiating across an enormous area. It contains motions from pulsation and convection. It carries absorption from molecules, scattering from dust, and subtle shifts from gas moving toward and away from us. Mixed into the observation is the influence of a smaller star that remained hidden beside one of the most studied objects in the sky. Astronomy has turned that light into a diameter, a temperature, a set of periods, a wind, a history of mass loss, a probable orbit, and a range of possible interiors. The remaining uncertainty is not emptiness. It is the boundary of what the evidence can presently support. One day, the boundary will move suddenly. Neutrinos will escape from the collapsing core. The shock will cross the swollen envelope. The familiar red point will brighten into a source visible by day and capable of casting shadows at night. Spectra will expose layers that are now hidden. Orion will change, and the star's long private evolution will become a public event across Earth. Until that day, Betelgeuse is not merely waiting. It is showing us how a massive star lives near the end, irregularly, violently, patiently, and on more than one clock at once. The supernova will be unforgettable because it will happen quickly. Betelgeuse is already unforgettable because we have learned to watch what happens slowly. For now, the shoulder of Orion still glows orange-red, and the old light continues to arrive. Good night.